Welcome back, fellow Night Owls. This is Dr. Nighttime, and tonight we're looking at a particular function that's rather difficult to differentiate. It's a piecewise defined function, and we're going to be looking for the derivative right at the point where things appear to go wrong. So consider the function f of x equals x squared times sine of 1 over x any time when x isn't 0, and f of x is 0 when x is 0. So let's first talk about why we realistically need a separate rule just for the case when x equals 0, right? Because when x equals 0, you try to take sine of 1 over x, right? And stuff goes wrong when you try to take 1 over x and then sine of that. But qualitatively, as long as x is close to 0, sine of 1 over x will still be somewhere between negative 1 and 1, because sine is always between negative 1 and 1, and then you're multiplying that by something close to 0. In fact, you're multiplying by that much twice, because of the x squared. So, fortunately, stuff doesn't go wrong here, right? So the function itself could be bouncing around a little funny, but at least in terms of continuity, it's behaved just fine, right? Whenever x isn't close to 0, then we don't have any continuity issues. The only time when we would have a continuity issue is at 0, and we can say, well, that's okay. Limit of f of x from the right equals limit of f of x from the left, which equals f of 0. Right? So as long as x is close to 0, then f of x will be close to 0, and when f of x is exactly 0, or when x is exactly 0, f of x will be exactly 0. So as far as continuity goes, it's actually continuous everywhere. But what about the derivative? So one naive approach you can take is you can try to use the rules of differentiation on the f of x function itself and see what happens in the limit as that approaches 0. So you say f of x equals x squared sine 1 over x. We differentiate that. So with product rule, we do x squared times derivative of sine 1 over x. It's going to be cosine 1 over x times negative 1 over x squared, if you remember your product rule and chain rule well enough. Right? And then plus the second half of it, right? Derivative of the first term times the second term, you get 2x sine 1 over x. Now, next cancellation that happens is you'll see the x squared. That's going to cancel out with the divided by x squared. So the 2x sine 1 over x doesn't go anywhere. This cosine 1 over x gets multiplied by negative 1, right? X squared divided by x squared. So you get 2x sine 1 over x minus cosine of 1 over x. And you can try to do a formal limit and show that as x approaches 0, this is not converging to anything. I'm going to use an informal argument to show that. Suppose that we want x close to 0. So let's say as long as it's 1 divided by a huge number, that'll get close to 0. So if I have 1 divided by 1 million pi, then I'll get 2 over a million pi times sine of a million pi. Sine of a million pi is 0. I then subtract out cosine of a million pi. Cosine of any even multiple of pi is just 1. Right? If you remember the way your cosine graph looks, it's 1 at 0, 2 pi, 4 pi, etc. It's negative 1 at pi, 3 pi, 5 pi, etc. So at a million pi, it's going to be 1. So you get 0 minus negative 0 minus 1, and that'll get you a negative 1. Then if I look at if I plug in 1 over a million and 1 pi for x, right? So I've picked two different values of x that are getting close to 0. And I crunch the numbers in there, and that gets me 0 minus negative 1, or 0 plus 1, which gets me a 1. And you realize I could pick 1 over any even multiple of pi and 1 over any odd multiple of pi, and that will still work. So just through an informal argument, I'm quickly explaining that that in the limit as x goes to 0, the derivative of this function does not converge to anything. So you might think, okay, derivative doesn't exist. But what happens when we try using the limit definition of the derivative? When we do that, if you remember, limit definition of derivative, f prime of x equals limit as x goes to 0 of f of x minus f of 0 divided by x. Or that'll be f prime of 0, rather. Typically, you'd say f of a minus f of x over a minus x. So this is a way of finding the derivative specifically at 0. And from that, okay, we know f of 0 is just 0. We know f of x is, as long as x is not 0 exactly, we know f of x is x squared sine 1 over x. We look at the difference, we divide by x, and we get the limit as x goes to 0 of x sine 1 over x. And there, we know that the sine function is going to be somewhere between -1 and 1. We are then multiplying that by x, and as x approaches 0, that means that our answer is stuck between -0 and 0. So it's going to go to 0. So using limit definition of derivative, we actually find that the derivative does exist at x equals 0, and the derivative itself is equal to 0. And so the question is, of these two methods that we've looked at, which one's the correct one? And the answer is the limit definition is the correct approach. If you wanted to take the derivative at any point other than 0, then you'd use this approach. You plug in whatever value you needed and get whatever number you needed. Right? Clearly, it doesn't work when you try this when x is 0 because we're dividing by 0, but that's okay because we can only say that we can only use this limiting argument when our function is, I would say, continuously defined. Here, where the function itself has a removable discontinuity, right? The limit of f of x from both sides goes to the same thing, and we just have to define f of 0 to be exactly what it would need to be to fill in the gap. That's called a removable discontinuity. When we have that, then yes, we do need to actually use limit definition of the derivative. This is a case of where the derivative exists at 0, but the derivative itself is not continuous at 0. In math textbooks and in math literature, you'll talk about the C1 class of functions being the class of functions whose derivatives of order 1 exist and are continuous. And you might think, well, how can you get, what sort of weird, wacky function would you need to have a derivative, but the derivative would somehow not be continuous, right? How does that work? And the answer is, well, what kind of nasty function do you need? You need a nasty function like this, like this sort of piecewise defined function here. Something like this is what you would need to have a derivative exist and not be continuous. So with that C1 function or C2 function where second derivative exists and is continuous everywhere, then that continuity requirement is just, it's precluding oddball cases like this. So realistically, on most functions that you'll have to deal with outside of when instructors want you to really understand about using limit definition, typically you don't have to worry about continuity of derivatives. As long as the derivatives exist, they're likely to be continuous. Weird stuff like this is the exception to the rule. As always, if you like the way I explain things and want to arrange private lessons, click the link in the description. And until next time, this is Dr. Nighttime, wishing you a good night.